Hey everyone, it's Kelly, and today we're going to do some examples on electron configurations. And essentially, electron configurations are just a device, like a summary to figure out where all of the electrons are around the nucleus of an atom. And it's kind of an accounting method or barcode, if you will, of each atom. And there's a way to do it. So we're just going to review that and do a few examples. So the typical structure is you need to figure out where your atom is on the periodic table, where like the sequence of orbitals that it takes to get there, and then how many valence electrons and core electrons are involved. So to review, on the periodic table you have your S block, those two columns, you have your P block, your D block, and then your F block down here. Okay, so in general, you're going to be just kind of be stepping your way through these, orbitals to figure out what your actual configuration is. And, the S block, you're going to read from the top left down to going to the right and down, and in increasing energy levels. So the S block starts with energy level of 1 and 2 and 3 and 4 and so forth. The P block starts with energy levels 2, 3, and so forth. And then, let's see if I can squeeze this in here. The D block starts at energy level 3, 4, and so forth. And the F block starts with energy level 4. Okay, so let's do a few examples to get the ball rolling a little bit. So our first example is oxygen. Okay, oxygen is fairly high on the periodic table. It's right here. A little bit of Where's Waldo when you're having to do more complicated ones. Okay, so we're going to start off by starting at hydrogen, essentially, counting off the electrons and the orbitals that we're dealing with. So helium's the weird funky thing where in general you're acting like it's over here, because that's how it works out. So the first energy level S block will be full. So you're going to start out by literally saying 1 S, and then there's 2 electrons, so it's a superscript 2. If we stop there, it'd be helium, but we're not done. We're going to keep going. Lithium and beryllium would be next, because we're just going down the periodic table. Those are also the S block, so energy level 2, but there's still 2 electrons because we're filling it. 1 electron per atom as we move across. Then the boron, carbon, nitrogen, and oxygen are on the P block. It's the first P block we've seen, so we're going to call it the 2p, right? But there's 4 electrons. And that's it. That is the electron configuration of oxygen. At this point, if the question asked you to create an ion, you would start taking electrons away from the valence shells. We'll get to some ions a little later. Let's keep doing examples though. Next, we're going to try phosphorus. Pause here if you want to try it on your own. Otherwise, we'll keep going. So everything is the same for phosphorus as it was for oxygen, but we're just going to add more to it. So we start at the beginning. We say 1s2, because that would be up to helium. 2s2 would be up to beryllium. 2p6 would get us to neon. But we're not done. We need to keep going down to now the energy level 3, and we're going to say 3s2. That would be magnesium if we stop there. But one more row, we're going to keep going to the P block. We're going to jump over to the P block, and we're going to say, there's aluminum, silicon, and phosphorus. So there's 3 electrons we're adding to the 3p3 block. Okay, this would be phosphorus. We'd stop there, box your answer, go home. Cool. Now let's keep going a little deeper in the periodic table. Let's go to orange maybe. So calcium, let's do calcium. Now instead of writing, because it's getting deeper in the periodic table, there's a lot of writing of all of these core electrons, okay? And let's try to do an abbreviated version, which is very acceptable. What you do is you find your atom of interest, back up on the periodic table until you hit the nearest noble gas. Okay, so backing up would go to potassium, and then finally argon. So argon is our nearest previous noble gas. So we're going to put it in a bracket. That's literally how we signify all of the writing of 1s2, 2s2, 2p6, etc. until that point. Cool. Now we can move forward. So if we got to argon, essentially, calcium is just 2 electrons away, and it's in the 4s2 block. Great. Now, what if I wanted you to do calcium 2+ ion? Okay. So what does 2+ mean? It means you're taking 2 electrons away from the system. Now, you're going to take it away from the valence shell, which is the s-orbital in this case. Okay. So we're going to literally strip away. So I'm going to rewrite argon and say 4s0. 2 electrons are taken away, right? But the way we actually write it in practice is we don't actually say 4s0. Okay. So that would be calcium 2+. It's essentially argon, acting like argon, the noble gas. Great. Let's keep going deeper into the periodic table. Let's try chromium. Where is chromium? There it is, right there. Okay, so it's still pretty deep, and the nearest noble gas is still argon, so I'm going to go ahead and write that in so I don't have to repeat all the core electrons that are unchanging. Now it gets a little weird. You might think, okay, I'm just going to do the typical thing that Kelly told me to do, 4s2. Now the D block starts at 3, so 3d4. You might think that. And that's a first guess, but this is when chemistry gets weird and says, nope, the rules we told you don't work in this specific case. And the reason why is all of these, orbitals, like the subshells, the Ds, the Ps, especially the Ds, this is where we're at right now, this is where it gets a little weird. It wants to be half filled or fully filled if possible. That's kind of its stable configuration. So if I kind of give you just a diagram here of the D shell, let me scoot that over a little bit. So we have 1, 2, 3, 4. Okay, that's of just the D shell. It would actually rather be this. And the way we do that is we take it from the s electron. Okay, so the way chromium actually exists, so it actually doesn't exist like that. Chromium actually wants to be argon 4s1 3d5. Because it wants to promote one to be a half filled, this is half filled d orbital block. Okay, half filled. The other, so that's the chromium column essentially. The other weird column in the D block is the copper column. It's for the same reason. It wants to promote to be fully filled, 10 electrons. So it takes 1 electron from the s orbital, brings it up, and essentially acts like zinc. Okay, so you want to make sure before you start making ions of these transition metals, because we're going to ask you about that, you need to create the correct neutral species and then promote or get rid of things as get rid of electrons or gain electrons as needed. Okay, so if I wanted to create an ion for chromium, so Cr+, we would look at this species, this electron configuration, the correct one, right? Before we actually take an electron away, which is what Cr+ means. So we're still at the argon, and we're going to actually take away from the 4s1 because the 3d5 is more stable configuration, and this 4s1 is kind of like a higher energy state, so we're going to take away from that first and essentially say 4s0 3d5. But as you saw earlier, let me rewrite that, a little weird. As you saw earlier, we don't actually write the 4s0, so really chromium plus is just saying argon 3d5. Okay, great. So this is some practice on electron configurations. Hopefully you found it useful, and keep practicing these because this really will never go away.